Clear? Now another interesting thing comes now into picture that in this rating given sizing problem is very simple. But if it is other way, that means I tell only m dot h, m dot c, th1 and tc1. Neither th2 nor tc2 is given. That means this is not rated. But I know A. This is known as rating problem. Two types of problems, sizing and rating. Sizing problem is the earlier one. The entire heat load is given. Q is known. That means explicitly m dot h, m dot c, th1, th2, tc1, tc2. Of course, these four are not required. tc1 is given, tc2, all known. Then we find out the area. We know the LMTD. So LMTD, using the LMTD method, we can find out. But if it is other way, area is given. Now this delta Tm is now LMTD. LMTD. Okay. And LMTD is what? LMTD is delta T2 minus delta T1 by ln delta T2 by delta T1. Okay. Now, if I know only these two, TH1, TC1, not TH2, TC2, this equation cannot tell anything. So how to find out this? We cannot know LMTD. So this type of problem where the sizing is given, but we have to rate the exchanger, means a particular exchanger with a given surface area is suitable or not, then what we have to do? We have to use an iterative method. That means the area is given, we have to rate the exchanger, whether it will be suitable. What is this rating? We have to assume. I will solve a problem today, it will be more clear, but still I am telling now, you can under either TH2 or TC2, any one we assume first. If you assume TH2, TC2 will be found out from this equation. Both are assumed value. Then you find out LMTD, obviously with this assumed value. Then with this LMTD, since A is known, we find out Q. Now with that Q, we iterate. That means we refine the value of TH2. Clear? So this way we do both TH2 and TC2 until they converge with each other. That means the new value is close to the earlier value. Very simple. So today it is nothing, but when it was discovered long back, there was no MATLAB, no program, even not a calculator even. So therefore people thought that it is tremendous stuff, an iteration method by hand, even without a calculator, whereas the sizing problem is explicitly found out with a slide rule even. It is not done. So therefore a difficulty was faced in this case, that LMTD method is not that suitable because it requires tedious iterations, and your gauge value is not very close. You have to go for number of iterations to convert the solution. Today it is a laughing stock, but it was there when it was discovered. Then two scientists, Case and London, they are two stalwarts in the field of heat transfer, they found out another suitable method for this type of problem where sizing is given, that means surface area is given. We have to rate the heat transfer in terms of its heating and cooling load. That means we have to tell what are the outlet temperatures of the hot and cold fluid. And this method, which was found by Case and London, is known as NTU-epsilon method. NTU-epsilon method. So LMTD is one method, another method NTU. An employer in your what is called that, your placement, placement interview will ask this thing only, that when NTU epsilon method will be used, when LMTD, what is the difficulty of LMTD in rating problem, and why NTU epsilon method is difficult for sizing problem, that also I will tell. Both the methods have relative merits, demerits. Now NTU epsilon method. Now what is NTU? NTU, I will tell you afterwards when the course of deduction it will come, But now you know the meaning of NTU, it is an abbreviation, number of transfer unit, NTU. And I will come this afterwards, because now if I write the NTU expression like Nusselt number HD by K, you will be nowhere to why unnecessarily all this, because automatically in the way of deduction a term will come which is a non-dimensional term known as number of transfer unit. Epsilon is known as effectiveness, which is also a non-dimensional term, effectiveness. And this effectiveness of an heat exchanger epsilon is defined as Q, that is the heat transfer actual by Q maximum, means ideal, that is the maximum. Actual discharge by the ideal discharge is the coefficient of discharge, this type of thing, the maximum and actual. What is actual heat transfer? This is this. M dot H CH, the temperature change. This is the actual heat transfer. But what is the maximum heat transfer which is possible? Now maximum heat transfer, if you write Q max, try to understand this. Again, there is a concept. Many people, you can make people nervous by asking one question. I will tell you that maximum heat transfer will be associated with the maximum change in the temperature. What is maximum change? That is TH1 minus TC1. That means, let us consider the counter flow. I will tell the maximum heat exchange will be possible when the cold fluid will attain the inlet temperature of the hot fluid. That is the maximum temperature available in the exchanger. Or other way, the hot fluid will be cooled to the inlet temperature of the cold fluid, which is the minimum temperature of the heat exchanger, which means that Qmax will be associated with the maximum temperature difference TH1 minus TC1 of the exchanger. But there is a clue. Hot and cold fluid physically will not attain simultaneously the TH1 minus TC1. It depends upon their capacity. That means the product of M dot and Cc. The fluid for which this M dot C is minimum, that will catch it first. Afterwards, the heat exchanger operation will stop. So therefore, it is written in a generic way, M dot C minimum, which may be either M dot C Cc, that I have to calculate from the value. I have to calculate from the value, the specific heat values and the mass flow rate values. Clear? That means the ideal or the maximum heat transfer is defined as minimum capacity rate or minimum capacity, that is mass flow rate times the specific heat capacity times the maximum temperature change. One thing, this is never achievable in a parallel flow. In a counter flow, like a reversible process, it can be achievable if we make an infinitely long exchanger. In a limiting case, like a quasi-static process, that in a limiting case TC2 will reach TH1 or TH2 will reach TC1 if you give an infinitely long. But here, even if you give an infinitely long exchanger, it will never reach. Delta S universe can be 0 in an ideal situation of reversible process, a quasi-static process, but can never become less than 0. It is impossible. So therefore, in a parallel flow heat exchanger, it is never possible, not feasible at all by the physics. So then what happened? This happens like that. This definition of effectiveness can be understood, conceived with respect to a counter flow heat exchanger. Nevertheless, as a criteria of comparing the exchanger with this effectiveness, we will use the same for parallel flow also, though it does not have any physical meaning like the ratio of actual to maximum heat transfer in that case. Is it clear to everybody? Good students? Okay. Now, if I consider the cold fluid is the minimum fluid, then what is epsilon? Now, if cold fluid, if M dot Cc is minimum, then what is this epsilon? It is, what is epsilon? You tell me if this is minimum, then m dot c Cc into Th1 minus Tc1. And in that case, I will prefer to write this Q, this equation. Why? Because this thing will cancel. Cc into Tc2 minus Tc1 cancels out. Similarly, if m dot HCH is minimum, then epsilon is m dot HCH in Th1 minus Tc1, and I will write then here this one, m dot Ch as Th1 minus Th. And ultimately this will cancel, Th1 minus Th2 divided by Th1 minus Tc1. So from here I can make another definition in terms of temperature change, which will be more convenient, and parallel flow exchanger will be little comfortable with this definition. It is the ratio of the temperature difference or temperature change of the minimum fluid means minimum capacity fluid, divided by the maximum temperature change of the exchanger. I think parallel flow heat exchanger will be much comfortable, that the definition via heat transfer is gone. That means it is the change of temperature for the minimum capacity fluid divided by the maximum temperature change available in the exchanger. Clear? Okay, very good. Now with this I will go for a simple algebraic deduction. Let us go back to our, what is that? To our earlier deductions, where we came here ln Th2 minus, now we consider the parallel flow arrangement again, Th2 minus Tc2 divided by Th1 minus Tc1 is equal to, if you I remember correctly, 1 minus u by a, just one step ahead, m dot c Cc plus 1 by m dot HCH, where after this was replaced from there and I got an expression for LMTD. But if I stop here in that deduction, I just change the root. Let us write this Th2 minus Tc2 divided by Th1 minus Tc1. You just follow. You may not have to take note because it is given in the textbook. You may or you may not take, but follow it. Because deductions, if you logically follow afterwards, also taking notes you can follow, then you will be able to deduce for a new condition, is equal to, just I write this thing in an exponential function, nothing great, minus ua, and here I will make some assumption before doing, because it is case by case. In a parallel flow, I first assume the cold fluid is the minimum fluid. That means m dot c Cc is the minimum. The catch you will know afterwards. First accept it. So here sir accepts that cold, this is minimum, the product is less than this product. Then I take this as common, m dot c Cc. When I will tell the case for which m dot HCH is minimum, then you will take m dot HCH as common. I will tell you. Then it will be 1 plus m dot c Cc divided by m dot HCH. Okay. Now we have to play with this. Now here, this equation is always used. Here what we will do, we will express Th2 in terms of Th1. What is that? Write that Th2 is equal to, from here, Th2 will be Th1 minus m dot Cc divided by m dot C, sorry, m dot hch, m dot ccc, m dot hch, Tc2 minus Tc1. I think I have done correctly. That means the trick is that Th2 is substituted in terms of Th1 and Tc2 Tc1. Th2 chalega nahi here. You will understand why. All these tricks will be understood at the end. Now, if you substitute this at the present moment, you accept that this way it has to be done. Only follow the algebraic continuity. Th2, then I can write here Th1 minus m dot ccc divided by m dot hch, Tc2 minus Tc1, Tc2 minus Tc1 minus Tc2, so Th2 minus Tc2 minus Tc2 divided by Th1 minus Tc1 is equal to exponential, this space is not utilized, UA by m dot ccc 1 plus this one, m dot ccc divided by m dot hch. So what I have done, the left hand side, Th2 minus Tc2, Th2 I have substituted by this. Okay. Now what I do, minus Tc1, here I am. That's why I am writing plus, because there is no place to write that. Some teacher intelligently, tactfully give a space. So minus Tc1 and plus Tc1. So what does it look? Th1 minus Tc1, okay, minus 1 plus this into Tc2 minus Tc1. So if you divide it by this, let me write that, Th1, oh God, Th1 minus Tc1 minus Tc2 minus Tc1, Tc2 minus Tc1 into 1 plus m dot ccc by m dot hch and divided by Th1 minus Tc1. Just follow it. Right hand side I am not writing. So this becomes is equal to 1 minus, since I have considered from this step, after approaching further, where this here approaching to this step, that the cold fluid is the minimum fluid. That means Tc2 minus Tc1 by Th1 minus Tc1 is the effectiveness, epsilon, because change in temperature of the minimum fluid divided by the maximum change in temperature. Clear? So therefore this will be 1 minus epsilon into 1 plus m dot ccc divided by m dot hch. This equals to this, exponential. So if you equate this and write this epsilon, then you will get this expression. Here I will write, where I will write this one here. Here, if you now equate this, 1 minus epsilon 1 plus this by this with this, you get finally an expression that epsilon is equal to 1 minus exponential minus UA by m dot ccc into 1 plus m dot c cc divided by, no sorry, what is that? Okay, m dot h divided by in terms of this quantity. Clear? Now, here m dot c cc is the minimum heat capacity. Now, this term minus UA by m dot c minimum is known as number of transfer unit, NTU, which is a dimensionless term. Overall heat transfer coefficient, surface area of the heat exchanger divided by m dot into c minimum. Now, if you can ask me the questions, you should ask this question to me without gossiping or chatting with your friends at the back. Sir, if the hot fluid is the minimum fluid, what could you have done? Now, if the hot fluid is the minimum fluid, first I tell you, this expression will be same, just m dot c and m dot h will be interchanging with each other, so that in a generic formula I can write in terms of m dot c minimum and m dot c, generic formula. So, this will interchange. If m dot h ch is the minimum, then it will be m dot h ch. NTU is minus UA by m dot c minimum. This will be NTU, and this will be 1 plus m dot c minimum by m dot c. Similarly, it will be 1 plus m dot c minimum by m dot c. But how to do it? Just interchange. Here I will start again. I started with cold fluid as the minimum fluid, hot fluid as the minimum fluid. I will take m dot h ch. This is not all. I will first take. Secondly, I will not TH2, that is the second catch. Here TH2 will not be substituted from this equation, TC2 will be substituted. And in that case, TC1 will not be added, subtracted. TH1 will be added and subtracted. This is having a rhythm. Good boys can understand this thing better immediately by intuition. Here we will take m dot h ch as common. Then it will be 1 plus m dot h ch by m dot c cc. Here TH2 will remain as it is. TC2 will be replaced in terms of other temperatures from here. TH2, TH1 and TC1. And after that I will add and subtract TH1. And in that case I will use the definition of epsilon as TH1 minus TH2 divided by TH1 minus TC1, because the definition of epsilon is the change of temperature for the minimum fluid and the change of temperature, maximum change of temperature available in the heat exchanger. Now, if you write in a very generic fashion, this will be like this. A generic expression is like this. If I make a very shortcut compact form by defining a parameter, just now if I define it like this, m dot c as the capital C, that means the capacity rate or simply the capacity, and m dot c, m dot cc, cc is the cc, and m dot h ch is equal to ch, and if I define C as the ratio of C min by C, which may be either this by this, that means this by this, or this by this, depending upon the case. In that case, the expression will be very simple. It looks like simple, expression remains same, 1 minus exponential minus NTU, where NTU is minus UA, sorry, not minus, sorry, NTU is a scalar quantity, dimensionless, m dot c minimum, that means c minimum with this nomenclature, where NTU is NTU into 1 plus capital C, and therefore here it is 1 plus capital C. This is the expression, where capital C is the ratio of the total capacity, that means m dot C, specific heat, ratio of the total capacity. What is the ratio? Minimum to the other one, that means C min by C. So this is the expression, and this expression is for parallel flow. Counter flow expression will be again a tricky, and that I leave to you to do the counter flow expression. In both the cases, that is left as an exercise, and the expression will be epsilon is equal to 1 minus exponential function of minus NTU into, here it will be 1 minus C, and here it will be 1 minus C into again exponential minus NTU into 1 minus. Now you see that in condensation and boiling, I told one of the fluids will be parallel. In case of condensation, the hot fluid is a parallel line. In case of boiling, the cold fluid is a parallel line. And parallel line means temperature does not change. And I told qualitatively that counter flow and the parallel flow remain same. But now mathematically you see that for a condensation and boiling problem, this one of the fluid specific heat tends to infinity. The fluid which is boiling and the fluid which is condensing, C infinity, I showed you earlier in the figure, which means that C is equal to C min by C. That means this higher C tends to infinity, because which tends to infinity, that will be always higher. No question of calculation. That means an intelligent boy will tell that for boiling condensation, the ratio which you denote as C will be always 0. And if you put C 0 in both the expression, we will yield the same value. Epsilon is 1 minus exponential minus NTU. This is the argument, NTU. If you put C 0, because the ratio is always 0, because the higher heat capacity rate, whatever we call the product of m dot C, is tending to infinity, which is a hot fluid, cold fluid ka mamla nahi hai. It is not hot fluid, cold fluid. Which one is higher, which one is lower? Okay, clear? But here one thing is very much open, that if I do not know the temperatures explicitly, then what we can do when we know the NTU, because area we know, overall heat transfer coefficient we know, and the mass flow rate and specific heat we know, we can straight away find out the effectiveness. And when the effectiveness is known, I can find out the temperatures. Clear? So therefore, this is a case where the rating will be done explicitly, no iterations. Rating means the size is given, we have to find out the heat transfer. That means all 4 temperatures are not known explicitly. Clear? Any problem? Okay. So we can find out the epsilon, and say, whenever we find out the epsilon, okay, TH1 and TC1, all right, chalega. Then from the definition of epsilon, I can find out the temperature difference of the minimum fluid. That means heat load aa jayega. The temperature difference of the other fluid will also come. So therefore, where rating heating load and cooling load is not done, but size is given, NTU epsilon method is an explicit method. To find out effectiveness, fatafat temperatures are found. But where the temperatures are given, sizing is to be made. LMTD is useful because from here, knowing epsilon, NTU as a function of epsilon will be little difficult. You understand? This may require tedious calculations or iterations.